This is section 8.2, integration by parts. This is another technique of integration that we're going to learn about. The main type of problem for which this will work is if you have an integral that involves a product. Generically, I'll just call it f of x times g of x dx. You might think this is called the product rule for antiderivatives, but it's not. It's got a different name. It's called integration by parts. And so we'll be splitting this up into parts of the integral to be able to proceed. You might think, for example, that it would be, well, I don't know what you might think. So I'll just go right on into it. So the basis of this is going to be the product rule as a derivative thing. So let's talk about what that looks like. If I have the derivative of the product u times v, we know, of course, that that's the first function times the derivative of the second function with respect to x, plus the second function times the derivative of the first function with respect to x. Okay? So that is a starting point for what we're going to do here. Now, one of the things that we can do with equations like this one that we have is we can integrate both sides of the equation with respect to x if we want to. And so we'll do that. Integrating both sides with respect to x. On the left side, the antiderivative of the derivative of something will give you back the original something, and that will have a c attached to this problem at some point, but for right now I'm going to just leave that off. And as it turns out, as long as there's still an integral in the problem, you don't need to introduce the c until all of the integral signs are gone. Okay, so I'm going to split the integral on the right side into two parts. And you might notice that the dv dx times dx will simplify to be u dv, and this will simplify to be v du. Okay, so because this is an equation, I can solve for any part of this by, say, subtracting something from both sides. So I'm going to solve for the antiderivative of u dv, which was on the right side. I'm just now pretending like that's now on the right, by subtracting from the other side. The other side was uv. I'm going to subtract that integral of v du from both sides. Okay, so I switched sides of the equation and I subtracted the integral of v du from both sides. And that right there is the formula for integration by parts. That's it right there. The trick in doing this process is going to be deciding which of those functions that you have in your problem, what are you going to call u and what are you going to call dv. This is the way I do this. It doesn't agree with what the book does exactly. It gives the same result, but I think of it differently. So when I have a problem, I'm going to first identify what dv will be by following this acronym. I'm going to find what dv is by paying attention to detail. And what that means is that this is an ordering of functions to check to see if you have one of those, then that's what you choose to be dv. So your choice, I'm sorry, for du. Your choice for du, no, it was dv. I was right the first time I said it. Sorry about that. All right, so the choice of dv is going to be if there's an exponential function in the integrand, that is your choice for dv. Anything else in the problem will be part of the u. If there's not an exponential function, your next choice for choosing something to be dv would be a trigonometric function. If neither of those two types of functions is present in the integral, then your third choice for a dv would be an algebraic function. And I'll review what I mean by each of these words in just a second. Then, failing any of those, your next choice would be an inverse trigonometric function, which I'm going to abbreviate trig. So I already wrote trigonometric once before. And then your very last choice would be a logarithmic function. Okay, so exponential functions are things like e to the x, 2 to the x, 10 to the x. Something where you have a constant raised to a variable power. Trigonometric, those are your 6 trig functions. I'll write a few of them: sine, cosine, tangent, etc. There are 6 of them. The other 3 are cosecant of x, secant of x, cotangent of x. Algebraic is powers of x. Radicals involving x, fractions involving x. So you could have like the square root of x squared plus 3 over x cubed minus 1, and that's algebraic. Okay, inverse trig, that would be something like arc sine of x, or cosine inverse of x. Those are inverse trig functions. And then logarithmic would be, natural log of x, or log of x, or log base 3 of x, or whatever logarithmic function you have. Okay, so that's going to be the order in which you would choose dv, leaving the rest of it to be u. So let's do an example of that, because I think that's really the best way for you to understand how to choose that. And again, my acronym detail, pay attention to detail and you'll be able to pick dv correctly. All right, so here's an example. Integrate x times e to the x. This rises to the level of, oh, I might need integration by parts because there's a product of 2 functions. So that's going to be my first thought. Oh, integration by parts because of the product. So I'm going to choose dv. I always write it first. In fact, the way I always write these is in a certain order on purpose. And it's because of something I do physically with my hand to make you understand the order in which to do things, which I'll get back to in a second. Okay, so is there an exponential function in this problem? Yes, e to the x, so that is my dv. And whenever you have a dv on one side, you have to have a d something on the other side. So we'll put the dx with the e to the x. And then what's left? What have we not used? I'm going to write that to the right of dv. The only thing left is x. Okay. Then, if you look at the formula above, we're going to need to know what u is and what v is, and what du is, because it's the very last thing in the problem. So if dv is equal to e to the x dx, think of integrating both sides, which I'm not going to write that step. An integral of dv will give you v, and the integral of e to the x dx, coolest function ever, is going to be e to the x. You know what? I just wrote this whole thing backwards. I just realized I never write it in this order. That's not the order I write it in, so I messed up. We haven't done anything wrong yet. I want to write it this right way. I'm going to put the u first, and put the dv over here. So I'm copying what I've already found, and put v here. Now, when you're integrating both sides, I know there's a plus c, but we're not going to put it here in this part that I'm writing, because we will attach it to the answer whenever we get rid of all of the integral signs. So I'm scratching that out because I had it in the wrong order. Even though I find dv first, I write it to the right of u. So I write dv down, figure out what that is, and then everything else is left to be u. I'll do a better job in the next example. Okay, so we're also going to need to know du, which is the very last thing in this formula up there. If u is equal to x, the derivative of u is equal to 1 times dx, which is dx. And again, if there's a d something on one side, it has to be a d something on the other. So there should be 2 dx's in this problem. One for dv, one for du. Okay, so what I do with my hand is to remember to multiply this. Up here, look at the box, u times v. I'm kind of holding my hand at a diagonal, and I'm going to multiply these two things together. Okay, so that's what I do first, is that that product, u times v. So I write u, which is x, times v, which is e to the x. And sometimes I'll commute those. You really want polynomials before exponentials, like e to the x following like x, or like I just wrote, or x squared e to the x, or whatever. Okay, minus the integral of v du. So hold my hand first of all at a diagonal so that I get the pink line product. Then I write minus integral of, and then I hold my hand horizontally, and that's going to be the product of those two things. So that's going to be e to the x dx. And your hope in doing this is that by splitting this into different parts, you've created something whose integral you do know how to find. Of course, the x e to the x is done. Minus, what's the integral of e to the x? Well, coolest function ever, it's e to the x. And now the very last integral sign has left the building, if you will. It's gone from the problem, and so at this point is the appropriate time to write plus c. And there's your antiderivative of x times e to the x. All right, so that's the process. As I promised, I will do a better job on the second one of writing things in the correct order. So let's go back. There were some examples at the outset, and we could do some of those, at least one of those. Let's do e to the x sine of x next. Okay, so I need to find out what u and dv will be. I'm going to start with dv. Pay attention to detail. My first choice for dv is an exponential function, like e to the x qualifies. So e to the x dx will be my dv. leaving sine of x to be my u. So I need to find du, which is cosine of x dx, and v is the antiderivative of e to the x dx, which is coolest function ever, e to the x. And so this will equal uv. So e to the x sine of x minus the integral of v du. So that's going to be e to the x cosine of x dx. Well, it looks like we've landed ourselves in a bit of a bad situation, because look at that. That one too is a product of two things. And can we use integration by parts successively? In other words, can we do it again? Sure. So we're going to identify u and dv for this part of the problem. There is an exponential function, so that's my choice for dv, which leaves cosine x to be my u. The derivative of cosine of x is negative sine of x dx. And the antiderivative of e to the x dx, of course, is e to the x. Coolest function ever. So the first part of this, the e to the x sine of x, that part's done, but the rest we still need to find. So after that subtraction, put a parenthesis, because our answer is going to be a binomial, uv minus integral of v du. So again, uv, notice how I write the order e to the x times cosine x. Feel free to commute those around if you don't like the order in which they appear. I actually did vu, but I always say uv. Okay, anyway. Oh, and this is kind of a silly thing, but when I first learned this, I thought of ultraviolet light uv minus integral of v du, which sounded kind of like video to me. So for some reason that just made sense to my young mind, and I remembered it that way at first. Then I found this physical way of writing it down correctly and doing the diagonal minus the product of the bottom line. Anyway, so we've done uv minus the integral of v du. So that's going to be e to the x times negative sine of x. That negative 1, I'm going to go ahead and pull it out in front. So minus a negative, we'll turn that into a plus. So I've pulled the negative out of the du, out of the integral, and it interacted with a subtraction to become addition. Okay, so writing the rest of it, sine of x dx. And that's another thing you'll probably do with some consistency, is you'll find that any constant in that v du, like a negative 1 there, you're going to find yourself going ahead and just starting by pulling that out of the integral, so you don't have to write an extra step just for that. Now be careful here, you are going to want to subtract, because you're going to distribute that subtraction through the parentheses. And that's why we wrote the parentheses, to make sure that everything got subtracted. Okay, so our original problem was, because I forgot where we started, I'm going to write it again, was what's the antiderivative of e to the x sine of x dx? And you may have been thinking as I was writing the second one, uh-oh, dude, you are going to be doing this forever, because it never will stop. And you're right, I could keep doing this forever and I would get awfully frustrated. But there's something that I hope you notice in the line I just wrote. Do you notice that this integral and that integral are like terms? So if I were to add that integral to both sides, that would have one on the left side plus the one from the right. That means I would have two of them over here. Which would equal everything else that was over there that I didn't move. And notice on the right side, the integral is gone. So I'm going to go ahead and write plus c, and I'm going to call this c sub 1. You'll see why in a second. Now, remember, we're trying to solve for this integral. So what would I do to both sides to get rid of that 2? Well, the answer, of course, is to divide both sides by 2. Or another way to say that is to multiply both sides by 1/2. Like this. Make sure you distribute that 1/2 to each term on the right side. And 1/2 of C1, half of a constant, is just another constant. So what I've done there is I've let C replace 1/2 of another constant, because it'll still be a constant, just half as much as whatever C sub 1 would have been. Okay, so if you look at the slide where it says integration by parts summary, common integrals, that's nice, and it's kind of nice to know what is a good idea to try. It falls in line with what I've already told you by saying pay attention to detail. So again, it doesn't hurt to know what they're saying there. I just don't think it's necessary to learn their way, because I think it's more complicated than what I'm showing you. In problems that involve, I'm on the next page, repeated applications of integration by parts, a tabular method might be useful. So I'm going to teach you the tabular method. I'm not talking about this particular problem. This one actually never goes away. The type that I'm talking about is going to be like another one from the first pages. So let me do that one now. It was x squared e to the x, which fits into this category nicely. So I'm going to do it this way, the way, kind of the straightforward way first, and then show you a tabular method as kind of a shortcut. All right, so paying attention to detail, my choice for dv is the exponential function, dx, leaving u to be whatever's left over, x squared. The derivative of x squared is 2x dx. And the antiderivative of e to the x, of course, is e to the x. So we're going to get u times v, so x squared times e to the x, minus the integral of v du. I see that 2, so I'm going to go ahead and pull that 2 out in front. 2x, then I'm going to write the e to the x dx. Just rearranging the multiplied things in the order in which I want to do them. So feel free to rearrange the order when you've got a bunch of multiplied things like that. Okay, looks like we need to do this again, because we still have a product here in the second integral. So pick a u and pick a dv. Paying attention to detail, exponential function e to the x times dx is my choice, which leaves x over here. So du is 1 dx, or just plain dx. And the antiderivative of e to the x dx, of course, is e to the x. And so that means that we have x squared e to the x from what we've already done, minus 2 times, and then this integral up here is going to be ux times v e to the x, minus the integral of v e to the x dx, which is our du. So distributing the subtraction of 2, so negative 2 times x e to the x. The negative 2 times negative 1 is positive 2 times that integral. So just distributed the negative 2. And then, of course, we actually have an antiderivative for that integral that's at the end of our problem. The antiderivative of that, of course, is e to the x, coolest function ever, all of the integral signs are gone, so right now is the appropriate time to insert plus c. All right, so now what I would like to do is I'd like to do this one, same problem, with the tabular method. So I'm going to still have to decide what I want my u to be and what I want my dv to be at the outset. So I would make the same choice. My u would be x squared. My dv will be e to the x. Notice in the tabular method I don't write the dx like I do in the normal process. Okay, so what you're going to do with those is you're going to take the u thing, whatever it is, and find its derivatives all the way down until you get to 0. So one aspect of this is that one of the two functions has to have eventually a 0 as the final derivative, and that's when you stop. So the derivative of x squared is 2x, the derivative of 2x is 2, the derivative of the constant 2 is 0. Then on the other side you find antiderivatives, and you go as far as the same level on the other side. So the antiderivative of e to the x coolest function ever is always e to the x, and I stop with the fourth one because that is the same number of things as I have on the left. Now, what we're going to do is we're going to take the first answer and diagonally go down. That's kind of what I was showing you earlier, that diagonal thing. And I'm going to put a plus sign on here, okay? And just know that in a second that's going to mean positive 1. I'll come back to that in a second. Then draw the next diagonal, put a minus on it. Next one, draw the diagonal, put a plus sign on it. And as soon as you've gone to the last one on the right that's in line, that's where you're going to stop. Okay, and what this means is you're going to integrate. I've already forgotten what the original problem was. I think it was x squared e to the x. Yeah, that's what it was. We're integrating x squared e to the x dx. And the answer is x squared times positive 1 times e to the x. So x squared e to the x. Then the next answer is going to be 2x times negative 1 times e to the x. So that's negative 2x times e to the x. Then the next one's going to be 2 times positive 1 times e to the x, which is plus 2 e to the x. And that's the last one. Put plus c, and you're done. Now compare these two answers. Are they the same? Yep. And so that's the tabular method. So let's do another one with the tabular method just to get some good practice with that. Let's do the integral of 4x cubed sine of 3x dx. Okay, so I know that the tabular method will work here because I'm going to choose my u and my dv using detail. My dv will be exponential. Nope, there's not one of those there. X cubed is not exponential, that's polynomial. It's a power of x. So not exponential, trigonometric, yes. That's trigonometric. Sine of 3x is trigonometric. And my u is going to be the 4x cubed. Okay, so because the derivatives of my u, if I keep taking them, will eventually erode down to 0. I should have written these down here instead of next to the u. I wasn't thinking of ahead. I was going to do the other way first, but I thought, no, we're going to go straight to the tabular method because that's what I want to practice. So I really wouldn't want to write that up there. Sorry about that. Okay, so take the derivatives of your choice for u all the way down to 0. So the derivative of 4x cubed is 12x squared. The derivative of 12x squared is 24x. The derivative of 24x is 24, and the derivative of the constant 24 is 0. Now the antiderivative of sine of 3x. I want to go off to the side here for a second and talk about this kind of thing in sort of a general way. So this is sort of separate from the rest of what we're talking about. What if we have the integral of sine of some constant times x, where our constant is just some number k? Well, we'll probably think, well, we're going to use u substitution, let u equal kx. The derivative of that is k dx. I don't have the k in there, so I'm going to multiply by k so it is there, times the dx, and have to multiply outside by 1 over k. And so we get 1 over k times the integral of sine of u du. And the antiderivative of sine, of course, is negative. So negative 1 over k cosine of u plus c, which is negative 1 over k cosine of kx plus c. So using that idea, isn't the antiderivative going to, for this one, going to be negative 1 over 3 cosine of 3x? Remember, we're not putting the plus c in this. Yep, that's right. Then what if I had the integral of cosine of kx dx? Let me use the same substitution. I need a k like I did last time. So I'm going to introduce the k and a 1 over k outside. So that becomes 1 over k integral of cosine of u du. The antiderivative of cosine of something is sine, so 1 over k times the sine of u. I'm going to skip a step this time. Sine of u, I'm going to take out the u and go ahead and put kx in its place, plus c. So the antiderivative of negative 1/3 of a function is negative 1/3 times the antiderivative of cosine of 3x, which according to the formula we just did, should be 1 over 3 sine of 3x. And simplifying, that's negative 1/9 sine of 3x. Okay. Then we need the antiderivative of that. So the antiderivative, we pull the negative 1/9 out in front. The antiderivative of sine of something is negative 1 over that k cosine of kx. That simplifies to be 1/27 cosine of 3x. And then the antiderivative of that is going to be 1/27 times the antiderivative of cosine of kx is going to be 1 over k sine of kx, which is 1 over 81 sine of 3x. Okay, so first one here times the second one there with a plus sign. Second one times the next one down diagonally with a minus sign. plus sign. Make sure you know what I'm pointing to. They kind of got off track a little bit. Minus sign and stop. Okay, so that means that this problem is equal to negative 1/3 cosine 3x times 4x cubed is negative 4/3 x cubed cosine x times positive 1, forgot to say that, cosine of 3x. Okay, now we're going to take our negative 1 times negative 1/9 sine of 3x times positive 12x squared is going to end up being positive, and 12 times 1/9 is 4/3 x squared sine of 3x. Okay, the next one's going to be 24x times 1/27 cosine of 3x, so that's going to be plus 24/27, which reduces to 8/9 x cosine of 3x. Okay, the next one we're going to have 24 times negative 1 times 1/81 sine of 3x. So that's going to be minus 24/81 reduces to 8/27 sine of 3x plus c. And that's that one. Okay. All right, so that is a tabular method, which is really nice if you have a polynomial times one of these functions like sine and cosine and e to the x, that their antiderivatives continue forever, and the derivative of the polynomial eventually becomes 0. This is a good time to use the tabular method. So if on the page before example 2, they have the types that are good for this, like a power of x times sine, a power of x times cosine, a power of x times e to the something. Those are all good. So let's do another one. This next one, it's going to be a lot like the one we just did, actually. But that's okay. Practice makes perfect. So for this one, the integral of x squared sine of 4x dx. Since this fits that form, I'm going to go ahead and start out that way. U and dv. The dv part's going to be the sine, of course, because trigonometric. Since there's not an exponential, trigonometric is a good choice for dv. Leaving the x squared over here. So take the derivative of x squared until the derivative finally becomes 0. Then the antiderivative of sine of 4x is negative 1/k cosine of kx. Then the antiderivative of that is negative 1/4 times the antiderivative of cosine of kx is going to be, I better write that down. I don't want to do too much in my head. 1/k times the sine of kx. So that's negative 1/16. Oops. Hold on. Make that look better. Okay, and the antiderivative of that is going to be the constant negative 1/16 times the antiderivative of sine of something is negative 1/k cosine of kx. So that's going to multiply to be 1 over 64 cosine of 4x. Okay, so do this diagonal product times a plus 1. This diagonal product times -1. And these signs, by the way, just keep alternating. I don't know if I said that earlier, but these diagonals go plus, minus, plus, minus, plus. You always start with plus, and it's always just plus, minus, plus, minus, plus, minus, plus, minus, alternating until you're done. Okay, so our answer is the product of x squared and -1/4 cosine of 4x is -1/4 x squared cosine of 4x. Then we're going to multiply -1 times -1/16 times 2. So that's going to be +1/8 x sine of 4x. And then we're going to multiply 2 times +1 times 1/64 cosine of 4x. So that's plus 1 over 32 cosine of 4x. That's the last one. We write plus c, and we are done. Okay. So that's a good example for us to have of another one with a tabular method. Okay, so let's try one. E to the t times cosine t dt. Now neither one of these will actually decay like the derivative of x squared last time decayed down to 0. Neither one of these will do that. So the tabular method is actually not called for here. So I need to pick a u and I need to pick a dv. Paying attention to detail, I do have an exponential function, so e to the t dt is my dv, leaving cosine of t to be my u. So the derivative of u is negative sine of t. Make sure since in this problem you're doing both derivatives and antiderivatives, be careful. The derivative of cosine is negative, but the antiderivative of cosine is positive. It's very easy to get those two mixed up with each other and give it the wrong answer, so be very careful. The antiderivative of e to the t, coolest function ever, is e to the t. So this is uv, so e to the t times cosine t minus the integral of v du. And the du has a negative, which I'll pull out. Negative times negative will make that plus e to the t sine of t. Anybody see what I forgot to write? Because I'll ding you on the test if you forget to write this. Du should have a dt. Like dv up there has a dt. So don't forget that, because it comes into play right here. You got to have that. Okay, so we get to play the game again. My choice for dv is still going to be the exponential function, e to the t times dt, leaving u to be sine of t. So du is cosine of t dt, and the antiderivative of e to the t, of course, is e to the t. So this original problem, e to the t cosine t dt, is now e to the t cosine t, which we got from our first step, plus, I guess we could put a parenthesis here, it won't hurt anything, but you need it if that's a subtraction still. Anyway, this is uv, so e to the t sine of t minus the integral of v du, which is going to be e to the t cosine of t dt. Well, if you distribute that plus through the parentheses, it won't change any signs behind it. So you might notice at this point that you have a like radical. It's not a radical, a like integral. And so what I'm going to do, like I did last time I saw this, is I'm going to add one of those integrals to both sides, which means I'll have two of them on the left side. And e to the t cosine t plus e to the t sine of t. And now put in your constant. And just like last time, I called that C1 because I'm going to multiply both sides by 1/2. I'm going to look back in a second and make sure we didn't do this exact problem, because that would really stink if I actually did the same one twice. This is what happens if I go off book and introduce something earlier than I planned to, because it made sense at the time. But anyway, I'll look and see, make sure it is or isn't the same thing. And then 1/2 times C1 will be just another constant, C. So let me take a look and see what we actually did before we did this. No, this was e to the x sine of x. So it was sine instead of cosine, and a different variable, but that's sort of a insignificant part of it. Okay, B. Oh, this is the first time we're doing one that's a definite integral. So let's look at this one carefully. 1 e cubed ln of x dx. Well, let's see. The antiderivative of ln of x, is that one of our basic 20? No, I don't see it there. So I can't think of any kind of trig substitution or form of 1 to multiply by or form of 0 to add or anything like split fractions. I don't see anything like that here. And this is a small category of functions that you actually do integration by parts with. You're thinking, I don't see two things there. Well, there's an invisible multiplier that you need to consider. Give you a second to think about it. What can you multiply by that's invisible? Yes, it's the number 1. So, choosing dv in the order that I mentioned is exponential. There is no exponential in the integrand. Trigonometric? Nope. Algebraic? Yep. 1 is algebraic. It's a degree 0 polynomial. So 1 dx, or just dx, is my dv, which leaves my u to be ln of x. So du is 1 over x dx, and v, antiderivative of 1, is x. So this is going to be uv, so x ln of x, and that part has come out of the integral, so that part needs to be evaluated from 1 to e cubed. That doesn't mean I have to do it now, but technically the x ln of x is outside of the integral sign, and it's going to be evaluated from 1 to e cubed. The rest of it, however, is still an integral. So uv minus the integral of v du, the integral from 1 to e cubed of x times 1 over x dx. Okay, so the first part of this problem is going to get ahead of the other part, which is just fine. So it will be e cubed ln of e cubed minus 1 times ln of 1. Okay, that's that first part. Minus the integral from 1 to e cubed of x times 1 over x is 1 dx. Okay, so let's see if we can simplify this sum. Starting at the end, ln of 1 is 0. 1 times 0 is 0, so minus 0 for the second thing that's minus 0. And then the ln of e to the something is that something, right? The ln of e to the a simplifies to be just plain a. So that'll end up being e cubed times 3. So 3e cubed minus 0, which I'm not going to write, minus the antiderivative of 1 dx is x, evaluated from 1 to e cubed. Move my screen down just a bit. Oops, that's the end of that space, so I gotta finish up here. So that's going to be 3e cubed minus, put e cubed in first, minus, put 1 in second, and then combining like terms, we are left with 2e cubed plus 1. Make sure you distribute that negative through to both terms. Okay, so that's the answer for B. So I'm going to need to close this down. For the last example, I'm going to need to go to, well, actually, let me think. Let me see if I can figure out how to make this work. I think I can make it work. So you're going to see something you haven't seen before. I'm going to go over here like that and do the next example, which is, I know it looks really weird, but I can handle it. Okay, C. Another definite integral from 0 to 1, tangent inverse of t. So I'm going to go through my list of 20 basic antiderivatives. I'm not going to find this one in that list. And this one, like the last one, ends up actually being in that small group of things where you're multiplying by 1. So let's pick our u and our dv by paying attention to detail. There's no exponential, right? There's no trigonometric because that's inverse trigonometric. Don't put that in the trigonometric category. That's an inverse trig thing. There's no trigonometric. Is there algebraic? Yes. Just like last time, 1 is algebraic. It's a degree 0 polynomial. So 1 dt is my dv. Everything else, i.e. tangent inverse of t, is my u. So what's my du? The derivative of tangent inverse of t is 1 over 1 plus t squared dt. And the antiderivative of 1 dt is simply t. Okay, so the antiderivative is uv, so t times inverse tangent of t, evaluated from 0 to 1, minus the integral from 0 to 1 of v du. And t times that will be t over 1 plus t squared dt. Okay, so that's going to be 1 tangent inverse of 1 minus 0 times tangent inverse of 0 minus, then for that one, I'm going to let u be 1 plus t squared. So du is 2t dt. So I have the essential part of that, t times dt, so I need to multiply by a 2 inside and a 1/2 outside. So I'm multiplying by a form of 1 to get my 2t dt to be my replacement for u. Okay? So this will be the integral of 1 over u, and of course the 2t dt all becomes du. Since this is a definite integral and it's now a du integral, we need to change our bounds. So the lower bound when t is 0 is the same as what u value. And again, when you do this, you have to pay attention to your substitution that you're making. That's how you're going to decide these lower and upper bounds. So substituting t equals 0 into that 1 plus 0 squared, u will be 1. So the lower bound is 1. And the upper bound t equals 1. Substituting 1 plus 1 squared, u will be 2 for the upper bound. Okay. So, I think I remember saying at least once before that everything you ever did in a prior course may come up in this course. So you need to know how to do tangent inverse of 1 without a calculator. Of course, that's pi over 4. I know 0 times something should be 0, but let's just double check how to find tangent inverse of 0, just by itself. Well, that is also 0. Minus 0 times 0 is minus 0. Okay. Minus the antiderivative of 1 over u du is ln of u. Actually, I should have said absolute value of u. Whoops. Let me make that look better. Absolute value of u. Evaluated from 1 to 2. So that's going to be pi over 4. Minus, putting in 2 first, the absolute value of 2 is 2, minus the natural log of the absolute value of 1, the absolute value of 1 is 1. The natural log of 1 is 0, and so this is pi over 4 minus the ln of 2. Okay, so oh, golly, I just figured out what I forgot. Way back up there. Easy mistake to make. I'm going to put this in red because I know I forgot it. This 1/2 here, I forgot to pull that down here. So I need to put in a 1/2 for all of these things because I messed up. There is a correct answer. Now, a lot of times if you have a multiple choice question, you may have done all this work correctly and you look at the answers and none of them look just like yours. So I want to talk about this a little bit in case you have a multiple choice question and your answer doesn't match any of their answers. All you need to do is maybe find alternate forms of the answer. So here are some alternate forms of that same thing, and I want you to see if you can remember these things and how you do them. One of them, I could write pi over 4 minus ln of 2 over 2. That's not vastly different. You might recognize that that's easily the same thing as our answer, so that may not confuse you at all. Here's another one. Pi over 4 minus the ln of the square root of 2. is the same as our answer. Why? Because if you have a number times the ln of something, you can bring that coefficient in as a power on the original argument of your ln. So a ln of b becomes the ln of b to the a, and 2 to the 1/2 is the same thing as square root of 2. That explains that one. How about this one? Pi minus 2 ln of 2 all over 4. Well, that's obviously the first answer I have inside of this box. Getting a common denominator by multiplying by 2 over 2 gets me this answer. And then here's one more, just for the fun of it. That's the same thing as pi minus ln of 4 over 4. That's using that same principle that we talked about over here. That'll become natural log of 2 squared from the last one we did. Natural log of 2 squared would be natural log of 4. So all of those answers are equivalent to our answer. And so that's a good thing to know how to do. All right, so that's the end of this lesson. I will see you in class.